Hello, and welcome to a brief overview of the production of butyl acetate, brought to you by Nicholas Garcia, Kate Richard, and Josh Miller. Now, for this project, we use this flow sheet as a general overview of what our design for the reactor should be. This is also cited right here. A more detailed version of the reactor can be found right here. The purpose of this project was for a non-engineer to get a rough estimate of the size of a reactor in order to produce butyl acetate. So as you can see here, this is the general outline of all of our code. So I'm gonna hit run on the program. First off, we have sulfuric acid that pops off. Now, in this project, we have several chemicals that have hazards associated with them. Some of those hazards involves to avoid inhalation, ingestion, and contact with the skin or eyes. In order to avoid this, proper protective personal equipment needs to be worn, such as a face shield, a full suit, vapor respiratory, and gloves. Now, some of the other chemicals involved besides sulfuric acid, which is seen up here, are acetic acid, N-butanol, and N-butyl acetate. All of these are flammable and need to have a chemical power for small fires and an alcohol foam system for larger fires. For small spills, you need to dilute it with water, then mop it up with the appropriate waste disposal. For larger spills, absorb using dry earth and non-combustible inert material. Then dispose of this according to the local state and federal regulations. All chemicals need to be stored and segregated in the approved area. Keep the containers in cool, well-ventilated area, and keep them tightly closed, sealed until ready for use. And should avoid all possible sources of ignition. Now, for this project, certain assumptions had to be made. First of all, the catalyst used has a density of 2,000 kilograms per meter cubed and a void fraction of 0.5. Another assumption is that the set conversion rate is 34% based on reaction kinetics. The last assumption is that it's equimolar initial flow rate. Now, so we hit run on our code now. We have a choice of a catalyst here. Now, the choice of this catalyst is very specific. However, other catalysts can be used. The choice of a proper catalyst for an esterification reaction is dependent on several factors. The most common catalysts used are strong mineral acids, such as sulfuric and hydrochloric acids. Lewis acids, such as boron, trifluoride, tin and zinc salts, aluminum halides, and organotitanates have been used. Cation exchange resins and zeolites are often employed also. In laboratory preparations, sulfuric acid and hydrochloric acid have been classically used as esterification catalysts. However, formation of alkyl chlorides or dehydration, isomerization, or polymerization side reactions may result. Sulfuric acids are widely used in plant operations but are less corrosive in nature. Phosphoric acids are sometimes employed, but it leads to rather slow reactions. Soluble or supported metal salt minimizes side reactions but usually require high temperatures than strong acids. With sulfuric acid, it makes the reaction reach equilibrium faster and is used in more continuous reactions, for butanol included. Other catalysts that have been found so far would be Amberlist 15. So, let's pick our catalyst. So, sulfuric acid. Now, there's a range of temperatures here given. I mean, obviously, for each reactor, we're going to need a different range of temperatures, but for this project, we chose 350 as the optimal one. And we have a molar flow rate given, and we chose around 170 to another optimal. So now, we've got this nice list of information. So as you can see here, we have our species, our input, our change, and our final amounts. Down below, we have the volume of the CSTR needed, which for this particular example is 4.01 meters cubed, with the reaction rate of negative 0.00409 kilomoles per second per meter cubed. Now, for our particular code, we also added the amount of energy that would be needed. And for this one, it'd be 89 kilowatts. And again, this is just a general idea for how a non-engineer would do this.